What is the role of simulation in VLSI? In this brief lecture, we will try to understand what is simulation, what is VLSI, what is simulation, and what is the role of simulation in VLSI. So agenda is what you define VLSI, what is VLSI, then what do you understand by Moore's law in VLSI, then what is the kind of policy adopted in a typical VLSI chip design, that is divide and conquer or divide and rule. Then what is simulation in VLSI, and what are the kind of simulation tools used in VLSI. So VLSI, as the name indicates, stands for very large scale integration. That means integration of passive and active components onto a single silicon chip. So the basic obvious advantages of VLSI is physically smaller size, lower cost, power consumption, high speed, and now of course there won't be any manual assembly. The important thing is lower cost and higher speed. So this Moore's law was a kind of a law which was a guiding principle for most of the evolution in VLSI. So this was based on a paper published by Moore in 1965. Basically, it was not a law; it was an observation that the component density in a typical chip will double every 18 months. That was a kind of prediction given by Moore's law. And incidentally, history has proven Moore's right. And so this is a historical. If you look into a typical microchips, like one is microprocessor over the years and a DRAM chip over the years, you will see that it was more or less followed Moore's law, and the cost per chip was coming down. Here, of course, is a comparison between the cost over the years, and the component density also, of course, had increased as per the Moore's prediction, or sometimes even it is more than Moore also has been achieved. So it is from a simple observation, it has evolved to a phenomenon because it has become a guideline for a target to be achieved for many of the microchip designers, and future technologies has to be targeted, had to keep Moore's law in mind. So it is a kind of a Ganesh worship for you as far as the chip design is concerned. So typically, the chip design being complex, a divide and conquer policy is used in various levels of hierarchy. That is, you start at the top level of the system and reach up to the silicon level. So you start with the specifications at the system level, and that is transferred to a silicon chip. So you have the board level design, chip level design, block level, logic level, transistor level, and the design level, the device level, and at each level you can parallelly do the various design process, and then so parallelism is very much used, and then that way a lot of time is saved, and finally as a system level engineer integrate all this. So it is like building a housing complex where you have parallelly doing many things, and then you finally have the housing complex. So simulation at each level of hierarchy, simulation can be employed to test the correctness of the behavior and testing. So simulation is a process of predicting the representation of the behavior or characteristic of one system through the use of some other system. You might have heard of flight simulators, car racing games, etc. But here, important thing is you are using computer. We are talking of computer-aided simulation or computer simulation, where the system is replaced by a mathematical model of that, and then computer becomes handy to analyze or simulate that system. So why do we simulation in VLSI? It helps us in prediction. It a lot of insight into the different behavior of the systems or the devices at each level, saves cost, reduces time to market, and modification and improvement at all levels is possible, and proposes new devices, logic, circuits, fabrication techniques, etc. And important things in the inside saving time and time to market, because your window is only 18 months. Moore's law says that you have to go for the next generation in 18 months time, so the window is only 18 months. So time to market is very important for your survival. So the kind of device simulation tools you can you can use computers to work, develop special software to simulate, which are known as tools. So then what we gain is automation, then the cost reduction, time to market, accuracy, because of course accuracy depends upon the type of mathematical model and the kind of computer hardware you are using. So because the more complex the model is, you need a higher CPU time, and then the accuracy will improve. So design better and more efficient hardware, and then consume more powerful simulation software. If you have efficient hardware, you can think of more better simulation softwares, and which in turn can help us in design better and more efficient hardware. So when you talk of simulation VLSI, you have two kind of things. One is ECAD and another is the TCAD, which is, or the technology CAD. ECAD is you start with the device level and end up with the system, where you might be using VHDL for describing the logic or system level. Then you have the circuit diagrams, then you have cell layout. As far as the component density you are encountering here is of a few millions or billions of transistors might be involved. Whereas in the TCAD, you start with the process and end with the single device. So hardly you deal with one device here. Like very often you will deal with a lot of physics, Boltzmann equations, Boltzmann transport equation, Schrodinger equations, etc. A lot of physics will be involved here. Then simulation varies. The TCAD, we are focusing on to the TCAD. So we can have equipment level simulation, you can have the reaction model. So at each level you have to develop the models corresponding to that. Then different IC processing steps can be also simulated, like lithography, different layers, deposition, etching, implantation, diffusion, etc. So which can give you the structures. Then you have the device level based on the device simulators, based on the basic device physics. So you can, from the device simulators, you can extract a lambda parameter model, or sometimes they are known as compact models, and which can be used in the circuit simulation. And then one can have even a package simulation also is possible, which can help you in finding out the self-heating operation with related to other chips, etc. And in fact, not only that, you need not restrict yourself to package simulation. You can simulate the whole fab design, for example, including the equipment placement, power and reactant supply, clean room environment. All those things can be simulated. So in a typical TCAD, this is one which shows the interrelationship between process, device and circuit simulators. You start with the fabrication information, which is fed into a process simulator, including the layout. Then the output of that process simulator will be a device structure, which will it includes the doping profile, the geometry, and then it is fed to a device simulator. And then the other input to the device simulator will be the terminal voltages, over which what kind of voltages will be applied to the given device. So then it will give you the device behavior in terms of the electrical characteristics. So then very often a parameter extractor is used, which will help you in the extracting the parameters which can be used in the compact model, which is very often used in the circuit simulator. The circuit simulator as such will contain many devices, but the device models which is used in device simulation and in circuit simulation are different. The device model which is used at circuit simulation level is known as the compact model. Typically in this other name for is the SPICE model, SPICE being one of the most popular circuit simulator employed. Then one of the TCAD tool which is popularly used in by industry as well as the academics is the Silvaco, where Athena is the process simulator, and Atlas is the device simulator, and Atmos is the parameter extractor. So this is a brief introduction to the simulation in VLSI.